Assalamu alaikum guys, welcome back. Today we will discuss determinants of the matrix and its properties and how we can use it. Last lecture we studied matrices, its properties, its operations, addition, subtraction, multiplication and so on. Determinant is also very important in linear algebra. We can make use of these determinants in a lot of places. So let's start with what the determinant is. A determinant of a matrix is a number, is a value that can be calculated from a square matrix. So first of all, your matrix has to be a square matrix, okay? So, and remember, it is a value. It is not a matrix, or it is not something rectangular. It's just a real number. And how we can define it, let's discuss starting from a 2 by 2 matrix. So if I take a 2 by 2 square matrix, then the determinant, which is denoted by this absolute value of A. But when we know that this A is a matrix, then absolute value means automatically that it's a determinant of A. Sometimes we write DET with A as well. You can write DET small for the determinant, and in the bracket you can write A. So it means this is the determinant of A, right? Or you can write absolute value of A. So both are the same. You can also write mod of the determinant, okay? So this is not mod of the determinant, mod of a matrix is a determinant of a matrix. So how we can find it? You multiply the diagonal entries A with D and write it here, and then you multiply off diagonal entries and subtract. Because it's a minus sign, so you have to be very careful that first product is diagonal and second product is off diagonal. Okay, so this is a real number. You see, yeah, when you multiply two numbers and subtract another number, you will get a real number. Similarly, we can define a determinant of a 3 by 3 matrix. There is no direct formula, so what we do is we convert this 3 by 3 into 2 by 2 matrices first. So what we do, we pick any row or any column, just one row or one column, not all of them. So let's pick first row. If I pick first row, what we will do, we will take the first number first, this number, right, and then remove the row and column. We will remove this row and this column, okay, where this A belongs. So if I remove it, the remaining determinant is EFHI, you see. So not the matrix, see, the determinant of EFHI. Then go to the second number B. Now if you go to the second number, then you have to remove this B. So you remove the row of this B and the column of this B. Okay, so what you are left? You are left with D, F and G, I. You see, D, F, G, I. And it will multiply by B. And similarly, go to the third one. Now remove the first row and third column. You will get D, E, G, H. Right? So you got D, E, G, H. Now the first one is plus, the second is minus, the third one is plus as well. Okay, so you start with the first one, so this with the plus one, the second with the minus, and the third with the plus. You see, the first is plus, second is minus, third is plus. Now you have three 2 by 2 matrices, and I know how to find 2 by 2 determinant of a 2 by 2 matrix. We will multiply E with I minus H with F. Similarly, B with I minus G with F, and so on. Okay, so these are the determinants of 2 by 2 and 3 by 3 matrices. We also define a cofactor of an element. A cofactor of any element in the determinant or in a matrix is obtained by deleting the row and column which intersect in that element with the proper sign. So what we do is, so it means I can say that this thing is also a cofactor of A. You see, this determinant is a cofactor of A. Why? Because I removed this row and this column of A and I got this remaining matrix here. Okay, with its proper sign. So it's a plus sign. Okay, so this is your cofactor of A. Similarly, this is cofactor of B with a minus sign. Cofactor of C is this. Okay, and it's not, these are just three cofactors. So for determinant, only three cofactors are enough, but we can define cofactor of any entry. Okay, so if I am picking a number, so let's say this is a matrix. If I am picking some number from ith row and jth column, let's say this is your number which is aij, ith row and jth column. So how I will get it? I will remove the column and row, ith row and jth column, and I will write the other numbers in a matrix form, right? Whatever you have, I will write this in a determinant with a proper sign. What is the sign? Sign comes from this I and j. So sign is this one. We take -1 to the power I plus j, ith row and jth column. So you see, if you go here, why we got plus here? Because this is first row and first column. So -1 to the power first row first column becomes 2. So -1 square is +1. Why this is minus? This is minus because it is -1 to the power first row second column. So it is 3. See, first row second column. So 3. Whenever you have power odd, you get -1. And this is again plus because it is first row and third column. So this is -1 to the power 4. Okay. So these are called the cofactors with its sign. Alright. So we can find all the cofactors, not just 3. I can find the cofactor of I as well. Okay, so there are 9 elements. We can find 9 cofactors of that. Okay, so these are cofactor of A, B and C, but when we find the determinant, we only consider one row or one column. So only 3 cofactors will be enough here. This is also called cofactor expansion of a determinant. Okay, cofactor expansion of determinant. So let's go towards properties of the determinants. What are the properties? The following properties are proved for determinants of the third order, but these hold for all determinants. Okay, we are proving them for 3 by 3 matrices, but they hold for any order, any square matrix, because determinant only exists for a square matrix. There is no determinant for a 2 by 3 matrix or 3 by 4 matrix. Okay, it has to be 2 by 2, 3 by 3, 4 by 4. Anyway, a determinant remains unaltered by changing its rows into columns and columns into rows. Okay, so it means you remember from the last lecture, when we when we change rows into columns or columns into rows, we call them the transpose of a matrix. So basically the determinant and its transpose have the same determinants. A matrix and its transpose has a same determinant. Okay, so if you change the rows into columns, columns into rows, nothing will change. So basically I can write this as the transpose of A has the determinant which is equal to the same as the determinant of A. Doesn't matter. Similarly, so this, you can see this example, a determinant is given and here the transpose of this matrix is given and the determinant is still the same, which is 10. If 2 rows or columns of a determinant are interchanged, the determinant retains its numerical value but changes its sign. If you change, let's say if you write first row as second row and second row as first row, 10 will remain 10, but the sign will change to -1. So it is the same determinant coming from here, but here you see we interchanged the rows and columns. Okay. So determinant, the first row and third column. First, see the first column come here in the third place. The third column comes here in the first place. Second remains the same. So if you change any 2 rows or any 2 columns, the determinant, this negative sign will change. Okay. A determinant vanishes if 2 rows or columns are identical. So if any 2 rows or columns are the same in your determinant, you can directly write it 0. You don't, here it's a kind of a proof that we started doing it and we saw it's 0 at the end. But if you recognize that the first column and the third column are both the same, exactly the same, 1 -1 0, 1 -1 0, you can directly write 0. Why? You can write 0 and write since first and third columns are the same. So they must give me the answer equal to 0. If each element of a row of column is multiplied by the same factor, then the whole determinant is multiplied by that factor. If you just multiply one row or one column by some number, the whole determinant will be multiplied by that number. So here you see in this above example, the first example, we multiplied this first row by 2. You see it's 130. We only multiplied this by 2, so it becomes 260. All other entries are the same. You see, the first row becomes 260, but all other entries are the same. You found the determinant. You see, the whole determinant value 10 got multiplied by this number 2. Okay, so if any one row or any one column is multiplied by some factor, the whole determinant is multiplied by that factor too. Okay, so these are 4 properties of determinants which are very useful. Now let's move on to inverse of matrices. Another topic, the next topic is inverse of a matrix. If a matrix is given, how you can find the inverse? You remember, let me recall something. If you have, you remember we defined multiplicative identity in last lecture. I said 1 is called the multiplicative identity. The reason is when we multiply 1 to any number, my number does not change. So in matrices we said that I is identity, matrix I whose diagonal is 1 and off diagonal is 0. So if you multiply any matrix with I matrix, identity matrix, you get your A back. So this is called the identity matrix. Now you multiply, what is the inverse? Inverse is if you multiply A with some number and you get answer as multiplicative identity. Is there any number? We know that yes, 1 over A is that number. When you multiply A with 1 over A, you get your A1 back. It means 1 over A is the inverse of A. 1 over A is multiplicative inverse of A. So here we want to do the same thing. We want to see, is there any matrix where I can multiply and get the identity? Identity means identity matrix now, not 1. Identity matrix. Is there any matrix here? This is basically the inverse of a matrix. This is the inverse of a matrix, and usually we write it A to the power minus 1. This is not the power minus 1. This is A inverse. Here A inverse, A to the power minus 1 in real number is the same as 1 over A, because these are real numbers. But here A inverse does not mean that 1 over A, because we have no division of a matrix. Okay, if you want to define the division by A inverse, you can do that. But you know that 1 over A is nothing. We have only multiplication of matrices. We don't have a division of a matrix. So division means taking the A inverse. Okay. So how to find A inverse? A very simple. If A is any matrix, then there exists A inverse such that when we multiply A with A inverse, it should give me identity, or A inverse with A should also give me identity. It means if you change the order, doesn't matter. In matrices, changing of the order matters. A into B is not equal to B into A. From last lecture, you remember, multiplication of the matrix is not commutative, so you cannot multiply them. You cannot change the order of multiplication, but here you can change the order, because inverse has this property. If you multiply A with A inverse, then they commute, then order does not matter, because both give you identity matrix, so they are equal and are identity. So any matrix who satisfies this condition gives you an inverse. Okay, so this is called the inverse of A. There are many methods of finding inverse. One very simple method which uses determinants is this. This is the formula. A inverse is equal to 1 over determinant of A. This is not 1 over A. This is 1 over determinant. You know determinant of A is a number. So I can divide by a number. And this is adjoint of A. Okay. I will come back to this one. This is adjoint of A. I will tell you how to find the adjoint of A. Okay. But before going to this one, I will give you some properties, and then we will find the adjoint of A. Okay, so let's discuss the properties. The inverse of a matrix is unique. You don't get more than one inverses. If A is fixed, its inverse, if it exists. Not all matrices have inverse, remember. If the inverse exists, okay, then it is unique. Second property, The reciprocal of the product of two matrices is the product of their reciprocals. Okay, so reciprocal mean inverses basically. We should not call it reciprocal. The inverse of the product of two matrices is the product of their inverses. Here reciprocal, because here you see I said if you want to define a reciprocal as inverse, you can do it. Okay, so you can define the reciprocal, but inverse is more appropriate here. If you write the inverse of two matrices, product of two matrices is the product of their inverses, but in reverse order. So if you take, you see, if you multiply two matrices and then take the inverse, it is the product of their inverses, but their order changed. You see the order has changed. B comes first and A goes afterwards. This is the property. They change their order of multiplication in reverse order. Multiplication by an inverse plays the same role in the matrix algebra that division plays in the ordinary algebra. As we said, let's say if you have 2 into x equal to 1, then how you find x? You divide by 2, right? You divide by 2, you get your x. So x is equal to 1 by 2. So here in this algebra, division played the role of finding this value of x. So if we are in matrix algebra, then if some matrix is multiplying by a vector and you are getting another vector on the right hand side, then you don't divide. Then A goes there and becomes inverse. Okay, because we said that inverse plays the same role as the division. So if you bring A to the other side, it will become A inverse times B. So that will be your x. Okay, so we cannot divide A on the other side. We have to take the inverse of A on the other side. All right, so that's why we said you can say that okay, this reciprocal is all A inverse, but keep in mind 1 over A is not the division. Basically it's not the reciprocal of a matrix, it is the inverse of a matrix. Even if you call it reciprocal, you should keep in mind that reciprocal of a matrix is basically the inverse of it. Okay. So what is the adjoint of A? For a 2 by 2 matrix, adjoint of A is very easy. Okay, for example, if A is your A, B, C, D, A, B, C, D. For a 2 by 2 matrix, adjoint is very simple. Then the adjoint of AB is A, D, J. Is adjoint of A, but in short we write ADJ only. Okay, adjoint. That is you change the position of the diagonal elements. A becomes D and D becomes A. Change the position and change the sign of diagonal sign. Don't change the position. B becomes minus B and C becomes minus. Okay, so change the sign of a matrix. Change the position of diagonal elements and change the sign of diagonal elements. That's the adjoint of a matrix B. Okay, for a 2 by 2 it's very simple. For a 3 by 3 it's not that simple. We have to take help from cofactors which we defined in the start. Anyway, let's do this example. This is A, B, C, D, right? 1, 2, 3, 4. If you want to find the adjoint of A, how you will find the adjoint of A? First of all, let's take because I need two things. I need determinant of A as well as the adjoint of A. Two things are needed. So let's find the determinant of A. Determinant of A is multiply 1 with 2 and multiply 5 with minus 2, right? So 1 with 2 is 2 and 5 into minus 2 is minus 10. And there is a minus sign from the formula. You remember AD minus BC. AD minus BC. So AD is this 2 into 1 minus BC is minus 10. So minus into minus 10 plus 10 becomes 12. What is adjoint now? Adjoint, I said change the position of the diagonal element. So 1 becomes 2 and 2 becomes 1. You see, 1 becomes 2, 2 becomes 1. And change the sign of diagonal. So minus 2 becomes 2 and 5 becomes minus 5. So we change the position of diagonal elements. We change the sign of diagonal elements. This is your adjoint. Now if I divide this adjoint by 12, 1 over A adjoint of A gives me the inverse of A. So A inverse is 1 over 10, 1 over determinant of A into adjoint of A. So you can divide everything by 10. So this is basically 1 by 5 right? 2 by 10 is 1 by 5. 2 by 10 is 1 by 5. 5 by 10 is 1 by 2. So minus 1 by 2 and 1 by 10. So this is the inverse. Now, can you prove that? Can you verify that this is actually the inverse? If we have to check our answer whether it is inverse or not, what we will do? We will do this. We will go back to the definition, this one. We will check whether if I multiply them, I get identity or not. So if you get the identity in both the cases, then it is the inverse of A. So if you multiply A with A inverse, you can check. You can multiply A with A inverse. You will see that the answer, after simplifying, you will see that the answer is identity. Okay, and not just this, you have to check the both A inverse with A as well. This will also give you identity. Okay, so let's see the product A with A inverse. 1 into 1 by 5 minus 2 into minus 1 by 2. Okay, so what is that? Is it 1 or not? So it is 1 by 5 plus 1. So 1 into 2 by 10, 1 by 5. 1 by 5 plus 1. 1 by 5 plus 1 is not equal to 1. It should be equal to 1. So something is wrong here. Where did we do the mistake? Yes, this is the mistake. It's 12. We have to divide by 12. 12 is your determinant, right? Not 10. So see, it's very important to check at the end your answer. So we made a mistake here. So I will change it in your notes as well and upload again. But if you have took the if you have taken the print of your notes determinant, just make the change. Okay. So here we have to divide by 12. So it's not 1 by 6, right? See, 2 by 12 is 1 by 6. 2 by 12 is 1 by 6. And 5 by 12 cannot cancel. So it will remain 5 by 12 and this will remain 1 by 12. Okay. Now if you multiply, you should get your answer equal to 1. So see, 1 into 1 by 6 plus 10 into, 5 to the 10 over 10 by 12. So 10 by 12 plus 2 by 12 is 12 by 12, which is 1. And now if you multiply first row with second column, it is 0. 1 by 6 minus 1 by 6 is 0. So now it is true. See, you can check both of them, it is true. So before that, we had a mistake here, and that's why this was not coming at 1001. So we divided by a wrong number. My determinant is 12 and we divided by 10 here. So it was a mistake. Just change it in your file as well. If you have not taken the print, then I will also change and upload. You can take the print of a new one. Similarly, it's another example. Second example, you can go through it, how to find the inverse, and again check at the end your answer. It's better to check it. Just take half a minute to check your answer to make sure. Now, finding the inverse of 3 by 3 matrix. I said for 2 by 2 matrix, adjoint is very easy. Okay, we can remember it. But for a 3 by 3 matrix, adjoint is not very simple. What is adjoint? You remember we defined the cofactor, right? So if I replace every number by its cofactor, what is the cofactor of this 2? Cofactor of this 2 is remove this row, remove this column, and take this determinant, right? So this is the cofactor of 2. So if I take the cofactor and replace this one, okay, so if I take the cofactor matrix, replace 2 by its cofactor. Cofactor is 4 3 the 12 minus 2. So this has determinant 12 minus 2, that is 10, right? So I replace 2 by its cofactor. Similarly, take the number 3 and take the cofactor. So for this cofactor, I will remove this row, this column. So 4 1 1 4, it's its cofactor. So 4 4 are 16 minus 1 is 15. So I replace this by 15, but it has a negative sign, right? 1 plus 1 minus 1 plus 1 minus 1 plus 1 minus so on. So if you take, this is a cofactor matrix, okay? We call it cofactor matrix, okay? So cofactor matrix. Now if you take the transpose of this cofactor matrix, you will get adjoint matrix. So the adjoint of A is the transpose of the cofactor matrix. You take the cofactor matrix and take the transpose, this one. Okay, so that gives you the adjoint matrix. So we have to find the cofactor of every one, and at the end we have to take the transpose of that, will give you the adjoint of A. So let's see this. A is given, so I know that A inverse is uh, this formula. So why we find this determinant first? Reason is we are dividing by the determinant, right? So if the determinant is 0, if the determinant of a matrix is 0, then we can stop here. We don't have to go ahead. We can say that there is no inverse. If this is 0, then A inverse does not exist. Do not go and find the A inverse. This will not exist, does not exist. Why does not exist? Because we cannot divide by 0. Simple is that. Okay, so determinant of A has to be non-zero for existence of A inverse. So if this comes out to be 0, just stop here and say there is no inverse of this matrix. So if A mod is not 0, then go ahead. So you see, adjoint of A is the transpose of the cofactor matrix. What is the cofactor matrix? We take the cofactor of every element. Okay, cofactor of A11, A12 and so on. So first of all, cofactor of the first one, as I calculated here, cofactor of the first one is 10, right? So how we got it? Cofactor, first cofactor is remove this row and this column and take these four numbers. These are 3, 1, 2, 4. So this is 10. Second was 15, but we have to put the sign as well, sign with it. Okay, so second is minus. So we already indicated this minus, so we are not writing minus here. But when I will write the cofactor matrix, I will put this minus. So plus minus plus minus plus minus plus minus plus. So you see, with this plus, left right up down all are minuses. With this minus, up down left right are all plus. Okay, so that's how we can complete all the cofactors. Now take the transpose of the cofactor. First row becomes first column, second row becomes second column, third row becomes third column. That's the transpose. So this is my adjoint. So we take the transpose of cofactor to get the adjoint matrix. Now after getting this adjoint matrix, I will just divide by the determinant of A. If you divide this matrix by determinant of A, you get the inverse. Okay, and again you can check this inverse by multiplying. You can check it here by multiplying your A, this A with this A inverse. You should get your identity matrix 1 0 0 0 1 0 and 0 0 1. All right, so check. It's good thing to check. If there is any mistake, you will see. So this is all about determinants of a matrix and using determinants to find A inverse. Next time I will give you a direct method of finding A inverse without using the determinants. Okay, these are called elementary operations on the matrices. So we will discuss elementary operations and we will use those row operations to find the inverse of A. And we can do many things with those row operations. Okay, so I'm stopping this lecture here. Determinant of a matrix, properties of determinants, how to find determinants of 2 by 2, 3 by 3 matrices, and then using the determinants to find the A inverse. Basically, we use determinants to find cofactors, and then after finding cofactors, we can find adjoint of A, and adjoint of A can be converted to A inverse. All right. Okay, till then, bye from me. See you in next lecture with elementary row operations.